So from chapter 4, at the end of it, the antiderivative stuff, that was leading us to the understanding of the integral, right? So it's the inverse of the derivative is the integral, really. And so what we're going to do now is take a geometric interpretation of that to better understand the area under the curve. Okay, that's the big thing in this chapter. It will lead us to the big lift for the rest of your calculus career. So in terms of importance, chapter 5 is huge. So you need to understand it, okay? I mean, I cannot stress that enough. You must understand chapter 5. Okay? All right, so here we go. So there are 3 types of approximations that we're going to do for the area under the curve. We're going to do a left, a right, and a midpoint rectangular approximation. And I'll explain that to you guys in just a bit. It should make sense, but we'll go through it. So for all of these problems, the function that we're going to use is f of x is equal to x squared, okay? And so what I'm going to do too to make our life simple is I'm going to tell you that our shift is going to be a shift of x moving 1 unit each time, okay? And so what I'm going to do is this is going to be my 1, this will be my 2 along the x-axis. This will be 1, 2, 3, and 4 in terms of the y-axis. So we know that this right here is the origin. All right? Any questions on that?
No.
Okay. So when I go to plot this, I know since the function is x squared, I know that at the origin it will be 0, 0. At 1, it's going to be 1. And that at 2, it's going to be 4, right? We know that the curve is going to look something like this, correct? All right. So in order to be able to dictate the area under the curve, when we use a left-handed approximation, so we're using a left-handed rectangular approximation, we're going to use the left endpoints of each delta x shift. And so I told you that the delta x shift was 1, right? So we're going to have one rectangle that's going to be from this width and one rectangle that's going to be created from this width. Does that make sense? All right. So in this first one here, we're going to look at the left endpoint of that delta x that we have. So the left endpoint would be this one right here at 0, right?
Yes.
Okay, so then from there, the area that's created by that being the height, it's got a height of 0 and a width of 1. So the area there is going to be 0 times 1. Understood? Okay. In the next shift, in this one here, I'm going to use the left endpoint. So at 1, I'm going to use the height of the function. So I'm going to use this point right here, 1, 1. And that's where I'm going to create my rectangle. So my rectangle is going to go boom, boom. Does that make sense? The reason that I use the point 1, 1 is because in that width of 1, I'm going to use the left corner of that width to find the height of the function. And where it hits the function is at 1, 1. And so this is the area that we will approximate it to be. So this would be the area that a left-handed approximation would give us. Are we okay with that?
Yeah.
The process. Okay. So what's the width of that rectangle that I just highlighted? It's 1, correct? So this has an area of 1. So the area of the 2 is going to be 0 plus 1. So that's going to be the area if I used a left-handed rectangular approximation for this. So is that a very good approximation of this curve, of the area under the curve? Not really, right? I heard someone say not really. So we can see that all of this area right here, all of this area right here, is not included in our approximation, right? But it is area under the curve. Agreed? Okay, so since that's the case, we know that this left-handed approximation is going to be an under approximation, right? And it's telling me that the area is 1. Clearly not accurate. But it's the process of understanding how to use the left-handed approximation to be able to get the area under the curve. All right, that was left. Now let's do right-handed approximation. So in a right-handed approximation, we're going to use the exact same points, the exact same curve. And now, again, with a width of 1, this is one width, this is the second width. Agreed?
Yeah.
So in the right-handed approximation, if this is the width, I'm going to use the right side to find my height. So where's my height going to be? It's going to occur at 1, right? So then my area is going to go back and over. Does that make sense? Because this is the height, this is the width. So I'm going to go a width of 1 with a height of 1. Understood? In this area here, this width, I'm going to have to use the 2 because I'm using the right endpoint to find the height. So this will be the height up here, correct? So then the area that's going to be created there, the result is going to be this. Okay? What do we notice? Do we have the area that we want under the curve? Did we cover all of the area under the curve?
Yes.
We totally did, right? But we did have a problem too, didn't we? We have too much, right? Now, in this case, we have an issue because all of this in blue is excess, correct? So is this right-handed approximation a very good approximation right now? Not really. We can see that in this case, this is going to be too much. This will be an over approximation, correct? So what's the area of the first rectangle that we got? The area of this guy is going to be 1. What's the area of the other one?
Still. And a half.
So this area think of it, this is the width, so that's 1. This is the height, this is 4. So this area should be 4, correct?
Yes.
So the total area is going to be 5 units, right? 5 units squared. This is an over approximation. So it isn't very, very good, right? We can see the left-handed approximation in this case with only 2 rectangles isn't very good. It was under approximating. And if we did a right-handed with only 2 rectangles, it was way over approximated. Let's see what we get if we do a midpoint approximation. So in the midpoint, again, we're going to use the same curve. I'm trying to be consistent so you guys can see everything that we're doing, right? So here, the delta x is still going to be 1, right? The width that we have is still 1. But when we want the halves, we're going to check for height at 1.5 and 1/2. So the values that I'm going to use are going to be this one and this one to create my rectangle. Okay, so the rectangle that's going to be created is going to be this one, and it's going to be this one. Okay, so now we see something interesting. The area, it's not going to cover all of the area under the curve, right? Clearly not. There'll be parts that are under approximated, but are there parts that are over approximated also?
Yes.
Yeah. So the under approximated piece is going to be the green. All right, so I'm consistent with the colors that I'm using. And the over approximated piece will be the blue. Well, we can find out the area. What's the area of that first rectangle? What's the area of this rectangle? So remember, the function was f of x was 1/2, correct? Or was a squared, x squared. So if I plug in 1/2 squared, what's the height going to be?
1/4.
1/4. So I'm going to get 1/4 times the width, which is 1, plus 1.5 is the same as 3/2. If that's squared, isn't that 9/4 with a width of 1?
Mm-hmm.
So that's going to give me 10/4 or 5/2, which is telling me that the area is going to be 2.5 for the area of this curve. Okay? So that's the process on how to find these areas. Okay?
Yeah.
All right, so I'm going to show you something cool. I'll talk about over and under approximations in just a second, but I want to talk about things in terms of a little bit of detail so you guys can see something. All right, so let's go to this one. We're going to use the same example. We're going to do all of them with the right ram, an R-ram. And an R-ram is a right rectangular approximation, okay? But the n that I'm going to use is going to be 2. And we did this one already, but I just want to take you through the basics of it. This was the right-handed approximation that I showed you. So remember, the width was 1, so it goes from 1 to 2. The values go up to 4, right, because they're by 1. So the rectangles that are going to be created, if it's got an n of 2, so over the gap from 0 to 2, it's going to have two rectangles. One rectangle is going to be this one, and the other rectangle is going to be this one. Right? We did this one. We just did it, right? We had an area of 1, an area of 4, and so the total area was 5 units squared, correct? Agreed?
Agreed.
Okay. Now, I want to show you that I can make more rectangles. So the bigger the n, the more the rectangles, okay? So I'm going to go 1, 2 again, same curve. Do you think that having more rectangles is better?
Yeah. It'll fill up the space a lot better.
Precisely. So we should have something at a half. We should have something at 3 halves. So we're going to have here a rectangle. We're going to have a rectangle here. We'll have a rectangle here. And we'll have a rectangle here. Does that make sense?
Yeah.
This still is too much area, correct?
Yeah, too much. Yes.
It's too much area, but we can find it. That's okay. We can find this area if we wanted. All we'd have to do is our n, since our n is now, what is our delta x in this case? So in this one we saw delta x was 1, right? That's how wide each rectangle was. How wide is each rectangle in this case?
Half.
Correct. That's important for you to notice. The width of the rectangle is half. Okay? So, when we go to find this information, we're going to get the function's height times the width, right? So the function's height at 1/2 is going to be 1/4, right? Because 1/2 squared times 1/2 plus 1 squared times 1/2 plus 3 halves squared times 1/2 plus 2 squared, which is 4 times 1/2. Agreed? Does everyone follow what I'm doing here?
Yeah, I'm catching on.
Wait, why'd you square the?
What's the function?
Oh, x squared. Yeah.
It's x squared. So because it's x
So
squared.
this is going to be available on YouTube, right?
Yeah. This is being recorded.
Okay, cool.
Yeah. you're all, I'm gonna watch this again.
Basically.
No, it's cool. And the thing is too is if you want to watch my lecture that I did last year on this, it's on YouTube too. So you can see if I did something slightly different last year in terms of maybe questions asked or something. It's up to you though. Now here, just so you guys understand what I did, I'll spell it out. So I went f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2 plus f of 2 times 1/2. And remembering that my function is x squared. Does that help?
Yes.
Okay. So then I should get 1/8 plus 1/2 plus 9/8 plus, and I'll just, to make my life easy, I'll make that 4/2. And then when I add these up, I should get 30/8, which is 4 3/4 for the area. Okay? Are we okay with that?
Yeah.
All right, I'm not going to do this one in terms of the math, but I'm going to show you something. The more rectangles we have, the better it's going to be. Okay, and if I'm doing right-handed approximations, this would be the first height. Here would be the next. Here would be the next. Here would be the next. And you can see, is there a lot of wasted space?
No. It's less.
Exactly. This becomes significantly less. So what I'm trying to demonstrate is the more rectangles, the better the approximation. Right? Eventually, what we find out is, you know, we did 1, we did 2. I think this one's going to be what? Something like 20?
Sure.
If you did 100, that'd be even better. If you go to infinity, guess what?
The best.
It's exact. So we can find exactly what the area under the curve is if we did an infinite number of rectangles. Isn't that cool?
Yeah.
So do you guys want to know what the area under the curve is from 0 to 2? I can do it.
Yes.
Here, I'll do it in my head. Let's see. Oh, here's what it is. It's 8 over 3. So what is that? 2 2/3? That's the exact area under the curve. So you can see that these others, that was significantly too high. This one was 4 4/3. It was still too high. See how this one was 5? When I did 2. When I did 4, it was just a little bit better. We look over here, we can see the midpoint was actually pretty good, wasn't it? For the actual approximation of the area under the curve.
Yeah.
So you can see the more rectangles, the better it's going to be. And I'll show you how to do that and find the area like that, but that's going to take some time.
So how do you know what approximation method to use? Left, right, or middle?
Your homework will tell you.
Oh, okay. It tells you.
Yeah,
Specified.
yeah. It's going to
Okay.
tell you if it's right, left, or whatever. Daniel, where do you want me to scroll up to?
Just like the first page.
Oh, you missed it?
Yeah, sorry, it's just on me.
All right. No problem.
Alright, I'm good now.
All right. So now I want to give you some Riemann sums that you're going to need. The math is going to get ugly. I will be honest with you, the math is going to get ugly. This homework is going to be a little bit tedious, but it's cool. So the crux to this first part, though, is understanding where do I find my height based off of left, right, or midpoint approximations. Okay? If you're using the left, you're going to always use the left-hand side of your width to determine the height, right? If you're using the right, you're going to use the right endpoint of your width to determine the height of the function for the rectangle. And then if you're using midpoint, you're going to find the midpoint between the width to find the height of the function to create your rectangle. Does that make sense to everybody?
Yes.
Okay, that's huge. All right, these Riemann sums are things that you should know from when you were in pre-calc. So you should have seen all of these before. So this first one with I is n times n plus 1 over 2. That's the formula for that. This one will be n times n plus 1 times 2n plus 1 all over 6. And I cubed would be n times n plus 1 over 2, that whole quantity squared. And then there's another one I want to give you, which is the Riemann sum of a constant is just going to be the constant times the number of terms being used. Okay? All right, so these are important for you to understand. Let's see. Okay, sorry. So here we go. Now, some things that are important that you'll need to know is this is the definition that will eventually lead us to the integral, which will actually find us the area under the curve, which is basically the inverse function of a derivative, or it's called the antiderivative, right? Like we did in 4.9. One of the things that's important for you to understand is that this right here, this delta x formula, is the width of our rectangle. Okay? So that's important. We see that delta x is throughout this whole function, so we can clean this function up to go like this. The limit as n goes to infinity of f of x1 plus f of x sub 2 plus f of x sub 3 plus da da dot, right? And factor out delta x because it's in all of them, right? Well, since we're talking about x1, x2, x3, x4, x5, the Riemann sum is adding up those terms. So I can go f of x sub I delta x, and that's like the clean way of writing this whole formula. Right? Because the Riemann sum is just telling us to add terms, right? That's what that E thing tells us to do, is add them up. Right? You guys remember that from pre-cal? All right. So let's put this into practice, because that's what you guys want to see, right? You want to see practical. Okay? So when we look at this problem, we can see the function. So I'm going to show you, you know how I told you the answer was 2 2/3?
Yeah.
I'm going to do all the math to show you the area under the curve. Ready? Do you guys have your TI 83s or 84s with you?
I have one. I'm learning how to use it still though.
Okay, so if you have it with you, have it out today, because I'm going to show you some shortcuts on how to be able to check your work.
Alright, cool.
So having your calculator with you today will be of big benefit. All right, so we know our function, right? Our function is x squared. What is this? The 0 here is the a for our interval, and the 2 is our b for the interval, right? So we're going from a to b, correct?
Yes.
Okay. So the delta x for this is going to be b minus a over n. Well, in this problem, I didn't tell you how many n's to have, so we're going to go with the very extreme general case. So I'm going to go 2 minus 0 over n. So I know that my delta x is going to be 2 over n. Okay? Another thing that we need, and this is a formula that you should know, x sub I is going to be my a plus I delta x. Okay? Where the I is this counting number that we're using here. It isn't the imaginary number. Don't get that confused. So then x sub I is going to be 0 plus I times 2 over n, or I'm going to clean that up to look like this, 2 over ni. Okay, so I have my delta x, I have my x sub I. Now I'm going to use that formula that I wrote up. So the limit as n goes to infinity of the Riemann sum from 1 to n of f of x sub I delta x. Okay? Now I'm going to do some substitutions. So the limit as n goes to infinity of my Riemann sum. Now my x sub I, the function f of x sub I is what?
2 over ni.
No. The function piece. This is the function.
Oh yeah.
But instead of x, I'm going to put x sub I. And this is my x sub I, correct?
Yeah.
But x sub I is this piece right here. So I'm going to go 2 over ni, but that's got to be squared. Agreed?
Agreed.
And then my delta x is 2 over n. Are there any questions to this point? Remember, I told you this is hugely important. So if there's something you don't get, ask now before I start to build. You guys are okay?
I actually have a question. So, the 2 over n is called the delta x?
Correct.
Okay. Oh, I see it. Sorry. Okay, never mind. Continue.
No, that's fine. You know, there's a lot of material here, so you're probably staring at the whole screen like, what the hell's going on? I get it. But yeah, it's a process, right? So I'm trying to go through the process slowly so you can absorb it. So if there's something you don't get, stop me, please.
Professor Montiel?
Yes.
Can you go over how you change the xi equals 8 plus I delta x? And how you come up with that?
You kind of broke up on me. Are you asking about this?
Yeah.
Okay, so this is a formula
Yeah.
where you're going to go, x sub I is always going to be equal to a plus I times delta x. Well, what's my a?
Your a here is 0.
0. So I'm going to go 0 plus I, and the delta x we found already was 2n, right? So then 2n times I is what's left. And that's my x sub I. Does that make sense?
Okay. Yeah, that makes sense.
Okay.
So you said the formula was a plus I delta x?
Yeah.
Oh, okay.
I times the delta x. Don't forget, they're multiplying. Okay, so then I'm going to square this. So I'm going to get 4 over n squared I squared, correct? Times 2 over n. So then that's going to become, and this is where algebra has become just going to be devastating. I'm going to get 8 over n cubed I squared. Agreed? Now, the 8 over n cubed has nothing to do with I, so I'm going to move it in front of the Riemann sum. So I'm going to get n as it goes to infinity of 8 over n cubed, the Riemann sum of I squared. But this should look familiar now. Right?
Nice. Oh, yeah, the second sum.
That's right. So then it's the limit as n goes to infinity of 8 over n cubed. And then this piece that's in blue is n times n plus 1 times 2n plus 1 all over 6. Agreed? So now we can play some games. So the limit as n goes to infinity, I'm going to go 4 over 3 n squared times n plus 1 times 2n plus 1. Does everyone agree with that simplification that I did there?
Yeah. Yes.
We can absorb that? We're getting that okay? All right. So then from here, I'm going to get 4 over 3n squared times 2n squared plus 3n plus 1. Agreed? All right, let me come up here. So that's going to give me 8 over 3. The n squareds are going to cancel. Plus 12. Well, let's just make the 3's cancel too. The 3's will cancel, so I'm going to get 4 over n plus 4 over 3n squared, and all of these are going to be the limit as n goes to infinity. Agreed?
Agreed.
So I'm going to get 8 thirds plus 0 plus 0 will give me 8 over 3, which is that 2 and 2/3 area that I told you before. And that is exact. This will be the area under the curve of f of x equals x squared from 0 to 2. Isn't that cool? Okay, you want to know how to check this?
Yeah.
All right, so pull out your calculators.
Right.
So this is for you to check with your calculator. So I'll write this down so you guys can see this again. Calculator. Check. So the first thing you're going to do, and this is for a TI-84, right? The first thing you're going to do is you're going to go to the upper left corner and go y equals. Okay, when you go there, you should be in the equation editor, correct? Type in x squared. Okay? Once you've done that, the second thing you'll do is you're going to go second trace. It's up. It's one of the bars up above, right? You guys see it? Third thing you're going to do is you're going to press 7. It should take you to your graph.
Right, yeah.
Then it's going to say lower limit. And you're going to press 0 and then enter. Then it's going to ask for an upper limit. You're going to press 2 and then enter. and then it's going to spit out the answer after it shades it as 2.666667.
Oh yeah, that's true.
Which is 2 2/3. That make sense?
How do you go between, like, what do you do after pushing 7?
It'll go to your graph,
Yeah.
and then it'll say lower limit, so you just type 0, enter. Then it'll say upper limit, go press 2 and then enter. And then it'll shade it and spit out an answer at the bottom right there of the screen with the graph.
So when you click trace and it gives you the graph, you push 7.
No. So when you go y is equal to x squared, you're going to go second trace. You're going to press second first, then trace. You shouldn't see the graph. You should see a list of things.
Yeah.
Then once you see that list of things, you're going to press 7. That's selecting the integral.
Oh,
And then it'll go to the graph and ask for a lower limit. You press 0, enter, 2, enter, and then it'll spit out the answer after it shades it.
Oh, okay, I get it. Cool, thank you.
Did you get it, Ray?
Yeah, finally.
Yeah. Cool. So it's second is a button.
Yeah.
Okay? So second is a button, then trace. All right. Do you want me to do a little bit more complicated problem so you guys can see more examples of this?
Yes.
All right, let's do another. And then you guys can check it with your calculators again, but let's say I gave you this. F of x is equal to 2x squared plus 1, and I want to go from 0 to 1. All right? Now, I'm not going to do it with the calculator. I'm going to do it manually, and then we can check it with the calculator if we'd like. What's the first thing that we need to find? What's that?
A and B.
Okay, A and B, but we have that. What's A?
0.
Okay, what's B?
1.
Okay. So then after we know that, because it's given to us in information, what's the first thing that we need to go find?
The delta x.
That's right. We need delta x. Before we can find x sub I, we need delta x because x sub I has delta x as part of it, correct? So then the delta x in this problem is going to be b minus a over n, which would be 1 minus 0 over n, which is 1 over n. Agreed? Now the second thing that we need is x sub I. So to find x sub I, again, it's a plus I delta x. But again, our a in this case is 0. So we're going to get 1 over ni. So x sub I is 1 over ni. Okay. The third thing, and I'm trying to be deliberate for you guys.
This is definitely helping.
Good. We're going to need to find x sub I. So f of x sub I is our function, right? And our function was 2x squared plus 1. But our x sub I is 1 over ni squared plus 1. Do we agree?
Mm-hmm.
All right, so now from here we can start this process. So the limit as n goes to infinity of our Riemann sum of f of x sub I delta x, that's the definition, is going to be this. The limit as n goes to infinity of this sum of our x sub I, which was 2 times 1 over n I, quantity squared, plus 1 times my delta x. And my delta x was 1 over n. Are we okay with that?
Yeah.
Here, I'll do this for you. Might help. Does that help you see it a little bit better?
Yeah.
All right. Okay, so now I'm going to do just the algebra expansion stuff. So this is going to be 2 times I squared over n squared plus 1 times 1 over n. So I'm going to get the limit as n goes to infinity of 2 over n cubed I squared plus 1 over n. Oops, I forgot my Riemann sum. Do we agree?
Yeah.
Okay, I'm going to break this up. I can distribute, so I'm going to go the limit as n goes to infinity of the Riemann sum of 2 over n cubed I squared plus the limit as n goes to infinity of the Riemann sum from 1 to I of 1 over n. Agreed? Do you agree with me?
Yes.
Yeah, split it up. So if you want here, this one is here with this one, and this one was this one. And then I distributed the limit with the Riemann sum like distribution. Okay? Since 2 over n cubed has nothing to do with I can move it in front of my Riemann sum. Same thing over here. 1 over n can go in front of the Riemann sum. What is going to be after the Riemann sum there? What goes there? What do you think?
Number 1.
A 1. Because 1 times 1 over n is 1 over n, right?
Yeah.
Okay. So the limit as n goes to infinity of 2 over n cubed, we know that the Riemann sum of I squared is n times n plus 1 times 2n plus 1 all over 6, correct?
Yeah.
And over here we know that the limit as n goes to infinity of 1 over n times the Riemann sum of a constant is the constant times n, correct? Which is just n. Do you agree with that?
Yeah.
Is there anyone that doesn't agree with that? I can point it out really quickly if you need me to.
Yeah, you pointed out.
Sure. So up here when I gave you the definitions, if it's a constant, it becomes the constant times n.
Okay.
And my constant was 1, so 1 times n is just going to be n. We okay? So this one over here is easy. Boom, 1. Now we have to deal with this. So I'm going to take the limit as n goes to infinity. I'm going to pull out the 2 and an n. So I'm going to get 1 over n squared times n plus 1 times 2n plus 1. Agreed? which is then going to be the limit as n goes to infinity of 1 over n squared times 2n squared plus 3n plus 1 plus 1, which is going to give me the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared plus 1.
Where did the 6 go?
Oh wait, thank you. This is a 3 here. Should be a 3. So this should be over 3. This should be over 3. This should be over 3. Okay? Because the 2 and the 6, that's going to have to give us a 3 in the denominator. So I'm going to get 2/3 plus 0 plus 0 plus 1, which is going to give me 1 and 2/3 units squared. And that's the area under the curve of this thing.
I have a question.
Sure.
So can you scroll up just a bit? Okay, so how come it goes from 2 over n cubed, and then I see like you divide the 2 and the 6 and becomes 1/3
Here?
n squared?
See this n?
Yeah. Oh, damn it. Okay.
No, hey, I'll tell you, it's subtle stuff, but that's where this right here in chapter 5 is the algebra tediousness that's going to happen. It's tedious. And so it's important that you guys see this. The detail of how you can easily make a mistake. I mean, look, I've been doing this forever, and I dropped the 3, right? I picked it up, but, when you're trying to fly through things, if you're not careful, you can make some major mistakes that cost you royally. So definitely take your time. Okay?
Okay, cool.
Can you scroll up just a tad bit more than just the beginning of the, right there. Right there.
Okay. You had the first part? Just let me know. I'll move it down as needed. No big deal.
No, I have that part.
Okay.
I see the beginning section.
Yeah, no worries. You want me to scroll up just a bit? You guys should check it while you have time. Check on your calculator. Let's see if you can get that same answer. May I scroll up? I don't know how much you needed.
Yeah, it's the same answer though. So.
You got it, Gerardo?
Yeah, it comes out to 1.66.
Yeah.
6.
Pretty sweet, huh? How you can check it with the calculator so you'll know if you're right. And can also be pretty horrible because when you don't get the right answer, you're gonna think, what did I do?
Oh, yeah.
It'll come for you, watch.
Yeah, it'll drive you nuts.
All right. Okay, let me do one more example. I want to do one that has some serious algebra involved in it for fun. So you guys can kind of see how tedious this can become. So here we go. I want to do another example. So this is y is x cubed, but now I want to go from 1 to 2. So it's no longer a is 0. Now my a is 1 and my b is 2. Okay? And I'll even tell you the answer. I already know the answer. It's going to be 3.75 or 3 3/4. Okay? So let's see if we can hit this. So first thing we want to do is get delta x. So my delta x is going to be 2 minus 1 over n, which will be that 1 over n. That's cool. My x sub I will be 1 plus 1 over ni. So now it's not so pretty, right? It's not something that is so clean. And I know that f of x sub I is going to be 1 plus 1 over ni cubed. And, well, I know that. That's going to be 1 plus 3 over ni plus 3 over n squared I squared plus 1 over n cubed I cubed. Right? Do you agree with that expansion?
Yeah.
Do you guys know how to expand quickly cubes?
And that theorem then.
What is it? The binomial
Trinomial
expansion theorem? No, forget that. You don't ever do it that way. So here, let me just show you something. This is just a side note for you, okay? To just be quick. If I go x plus, let's just call it x plus some constant, okay? To the 0. Anything to the 0 is going to be 1, right? Except for 0. X plus a to the 1 is going to give me coefficients that are 1 and 1. This is Pascal's triangle. I'm just looking at the coefficients, okay? X plus a squared is going to be 1, 2, 1. Do you know how I'm getting these numbers? Have you ever seen Pascal's triangle before?
Yes.
Okay. And then this one's going to be 1, 3, 3, 1. That is how I got 1, 3, 3, 1. Now, the powers go like this. Okay? X was first, so that's the highest power. It's to the third. The a would have been to the 0. Coefficient is that 1 that we've got. Since it's plus, it's going to stay plus. Then I'm going to have the coefficient 3 that we have. The x is going to drop 1 power. The a is going to go up a power. Then it's plus again. Coefficient's 3 from the Pascal. x is going to drop a power, a is going to increase a power. Then the coefficient is 1, x will be 0, x to the 0, and a will go to 3. So when I do this, that's going to go, since it's a 1, it's not that interesting, but it would have been 1 cubed, 1 squared, right? So 1 cubed times 1 over ni to the 0, that's 1. Then I would have gotten 3, which I have, 1 squared, which is 1, and then this piece to the first power, so 1 over ni. You see that?
Yeah.
Then here it would have been 1 to the first power with the 3 in front. Then this piece would have been squared, so 1 squared would be 1. That'd be n squared I squared, n squared I squared. You see that? And then 1 to the 0, who cares? There's a coefficient of 1, and then this piece cubed. So 1 cubed over n cubed I cubed. Makes it fast. It's just a pattern. Instead of trying to bust out the binomial theorem. Oh, that's...
Just this Pascal's triangle?
Yeah. Yep. Okay, so using that information then, I'm going to get the limit as n goes to infinity of this Riemann sum of f of x sub I, which we have, and I'm going to use the expanded form of it, okay? 1 plus 3 over ni plus 3 over n squared I squared plus 1 over n cubed I cubed times the delta x, which was 1 over n. Agreed? So then when I distribute through, I'm going to get the limit as n goes to infinity of the Riemann sum of 1 over n plus 3 over n squared I plus 3 over n cubed I squared plus 1 over n to the 4th I cubed. Agreed? Do we agree?
Yeah.
Okay. Then I'm going to break it up to each. So the limit as n goes to infinity of the Riemann sum of 1 over n plus the limit as n goes to infinity of this Riemann sum of 3n squared I plus the limit as n goes to infinity of the Riemann sum of 3 over n cubed I squared plus the limit as n goes to infinity of the Riemann sum of I cubed. Agreed? Now, this has nothing to do with I, so it's going to be going in front. So the Riemann sum of a constant is just going to be n, correct?
Yeah.
So I'm going to get 1 over n times n, right? The 3n squared is not going to matter. I'm going to have the Riemann sum of I, and the Riemann sum of I is n times n plus 1 over 2, correct? Plus the 3 over n cubed has nothing to do with I. So now I have I squared. I squared we've done now like 10,000 times. Agreed? And then I cubed we did is going to be n times n plus 1 over 2, that whole thing cubed. Agreed? Oh, I left out the one thing I left out in this one. See how easy it is to make a mistake? I left out the n to the 4th I cubed, so this should be n to the 4th. Agreed?
Yeah.
Okay. So this is 1. This one here is going to be 3 over 2 n times n plus 1, plus this one will be 1 over 2 n squared times n plus 1 times 2n plus 1, plus this one's going to be 1 over 8n Is that right? Oh wait, this is not cubed, it's squared. You people need to help me out. That's a square. So I'm going to get, the n's are going to cancel, that's going to be n squared, so that's going to be 1 over 2n squared times n plus 1, that quantity squared. Agreed? Ooh, that's a 4, that's a 4. Okay, so then 1 plus 3 over 2 plus 3 over 2n, and ooh, let's not forget, all of this is going to infinity. Still, all of this is going to infinity. All of this is going to infinity. Okay, this middle is going to be, I'll write it down so you guys can see. So 1, 3 over 2 to the n, plus 1 over 2n squared, plus 1/4 plus 1 over 2 to the n, plus 1 over 4n squared. All right, are you okay with that? Does everyone see how this was a 4?
Yes.
Because the 2 squared becomes a 4. Okay, just making sure. All right, is everyone okay with how I got to this?
Yeah.
All right, something cool. As the limit goes to infinity, anything that has n in the denominator is going to end up being 0, right?
Yeah.
So that's gone. That's gone. That's gone. That's gone. And that's gone. Agreed? So we're going to get 1 plus 1.5 plus 1 plus 0.25, which is 3.75. Which is the answer I told you it was going to be, right?
Right, yeah. That's what the calculator says too.
Yeah. But do you guys see where there's so much room for mistake?
Yeah, you have to go kind of slow a little bit.
Oh yeah, be very careful when you're
Yeah.
doing this. Be very careful. This will take time. And so it's being meticulous about every single step so that you can be successful with this. All right?
Got it.
Any questions on this problem?
No.
There's 5.1. All right. Do you have any homework questions then? I'm done with 5.1.
I have a question. More of a question.
From the homework?
It's an example in the book.
Oh, okay, no problem. Here, let me stop recording, and then these will just be notes that are in the notes, okay?